On February 27, 2026, engineers at NASA's Jet Propulsion Laboratory commanded Voyager 1 to perform a routine maneuver. It has executed countless times before, a simple role designed to recalibrate the spacecraft's magnetometer, one of only 2 scientific instruments still functioning after nearly 50 years of continuous flight. This exact maneuver had been performed safely many times throughout the mission's history. It was not supposed to be dangerous. And then, without warning, Voyager 1's power levels dropped unexpectedly, dropping fast enough and far enough that engineers realized, in the hours that followed, that any further decline could trigger the spacecraft's own automated undervoltage fault protection system, a built-in safety mechanism that, once activated, would begin shutting down onboard systems on its own, with no ability for anyone on Earth to intervene directly or predict exactly which systems it might choose to sacrifice first. This is the real story of the moment. A routine operation on humanity's most distant spacecraft nearly became a genuine crisis. Why NASA was not fully prepared for what happened next, and the difficult, permanent decision engineers were ultimately forced to make in response. This was not, it is worth noting immediately, the first time in recent years that Voyager 1 has caught its own engineering team off guard. In May of 2022, NASA disclosed that the spacecraft's attitude articulation and control system, the onboard system responsible for keeping Voyager 1's antenna precisely aimed at Earth, had begun, returning telemetry data that simply did not match the spacecraft's actual physical orientation, a discrepancy engineers could not immediately explain. Then, starting in November of 2023, an even more serious problem emerged when Voyager 1 began transmitting a steady, otherwise healthy radio signal that, once it reached Earth, contained nothing but unreadable, scrambled data. It took engineers months of painstaking remote diagnostic work, conducted entirely across a communication delay exceeding 22 hours in each direction, to eventually trace that specific failure to a single corrupted section of memory within one of the spacecraft's 3 onboard computers, ultimately resolving the issue by relocating the affected code to a different, still functioning section of memory in the spring of 2024. Both of these earlier incidents shared a common thread with what happened again in February of 2026, a spacecraft old enough and far enough beyond any previous engineering experience that entirely new kinds of problems keep emerging, each one requiring the current mission team to improvise a solution nobody could have specifically planned for in advance, because nothing quite like it had ever happened to any spacecraft before. To understand why this specific event genuinely caught the mission team off guard, you first need to understand exactly how precarious Voyager 1's operating margins have become after nearly 5 decades in space. The spacecraft draws its electricity from 3 radioisotope thermoelectric generators, sealed units that convert heat from the natural radioactive decay of plutonium-238 into usable electrical power. This process cannot be paused, refueled, or reversed in any way, and both Voyager spacecraft lose approximately 4 watts of available power every single year. A slow, steady, entirely predictable decline that engineers have spent decades planning around, carefully deciding which instruments and systems to prioritize as the available power supply continues shrinking toward its eventual, inevitable end. At launch in 1977, these 3 generators produced approximately 470 watts of power combined, roughly enough to run a couple of modern kitchen appliances simultaneously. By early 2026, essentially 5 decades of continuous radioactive decay had reduced that same output to somewhere in the range of 250 watts, spread across every heater, transmitter, instrument, and control system. The spacecraft still needs to keep functioning correctly in an environment where outside temperatures sit only a few degrees above absolute zero. This gradual decline forces a very particular kind of engineering discipline, one considerably different from managing a spacecraft with power to spare. Every watt currently running through Voyager 1 has already been carefully accounted for, weighed against every other system competing for that exact same shrinking resource. There is no meaningful reserve capacity left to absorb an unexpected surprise, which is precisely why a specific maneuver that had previously produced a small, predictable, easily tolerated fluctuation in available power could, once the spacecraft's overall margins had shrunk far enough, suddenly produce a response serious enough to threaten triggering the fault protection system entirely. At the time of the February 2026 incident, Voyager 1 was already operating with only 2 of its original 11 scientific instruments still functioning, running on a fraction of the electrical power it carried at launch in 1977, with every single watt already carefully accounted for and allocated. The roll maneuver itself was intended purely as calibration, a brief, controlled rotation allowing engineers to verify the magnetometer's readings against a known reference point, a standard piece of housekeeping the mission team had carried out successfully many times over the decades without incident. What actually happened during this specific maneuver was not something engineers had specifically planned for or expected. Voyager 1's power output dropped in a way that did not match prior experience with this exact procedure, and the specific severity of that drop meant the spacecraft was, for a period of time, sitting, dangerously close to a threshold that would have triggered its undervoltage fault protection system automatically, without any command from Earth required to set it in motion. Understanding why this specific possibility genuinely alarmed the engineering team requires understanding exactly what a spacecraft's fault protection system is actually designed to do, and why its automatic nature makes it simultaneously essential and genuinely unpredictable in a situation like this one. Fault protection systems exist specifically because a spacecraft this far from Earth cannot wait for a decision from mission control before responding to a genuine emergency. Any command sent from Earth to Voyager 1 takes more than 22 hours to arrive. And any response takes an equal amount of time to travel back, meaning a spacecraft experiencing a genuine, rapidly developing electrical crisis simply does not have the luxury of waiting nearly 2 full days for human engineers to diagnose the problem and issue a considered, careful response. To address this, Voyager 1, like virtually every deep space mission, carries on board software specifically designed to recognize dangerous conditions and react automatically, shutting down selected systems on its own initiative in order to protect the spacecraft's overall survival without waiting for permission from Earth. This automatic protection logic was written and programmed into Voyager 1's onboard systems decades ago, using the engineering, assumptions, and priorities that made sense for a spacecraft still in the middle of its primary planetary tour of Jupiter and Saturn, long before anyone involved in the original mission design could have seriously anticipated the spacecraft would still be operating in an entirely different operational context nearly 50 years later. That original programming has been patched, updated, and carefully worked around by generations of subsequent engineers as the mission has evolved, but the fundamental decision-making, logic embedded in the fault protection system remains, in important respects, a product of 1970s-era priorities, applied to a spacecraft now operating under conditions its original programmers never specifically designed for. This is exactly what makes a scenario like the one Voyager 1 nearly triggered in February 2026, so genuinely unnerving for the team managing the mission. If the undervoltage fault protection system had actually activated, it would have begun shutting down onboard systems according to its own internal decades-old programming logic, systems that might not necessarily align with what the current mission team, informed by nearly 50 years of accumulated operational knowledge, would have chosen to prioritize themselves. There would have been no opportunity to intervene in real time, no ability to select which specific instrument or subsystem got sacrificed first, and no guarantee that whatever the automated system decided to shut down could ever be successfully restored afterward. In a spacecraft this old, running on margins this thin, an automated response like this genuinely carries the risk of doing lasting, irreversible damage to the mission, precisely the outcome the engineering team spent the following weeks working urgently to avoid. Faced with this newly revealed vulnerability, NASA's engineering team made a difficult, deliberate decision. Rather than wait for a future maneuver or unexpected event to potentially trigger the exact same dangerous power drop again, possibly with less warning or a less favorable outcome, they chose to proactively reduce the spacecraft's own power demands, creating a larger, safer buffer against any future, similarly unexpected fluctuation. On April 17, 2026, engineers at the Jet Propulsion Laboratory sent a command permanently switching off Voyager 1's low-energy charged particles experiment, an instrument that had been operating almost continuously since the spacecraft's launch in 1977, very nearly 49 consecutive years of uninterrupted scientific service. This particular instrument had provided genuinely valuable, irreplaceable data throughout Voyager 1's journey, measuring the low-energy charged particles, including ions, electrons, and cosmic rays, that make up the actual physical environment of interstellar space, exactly the kind of direct, in situ measurement no ground-based telescope or any other existing spacecraft is currently positioned to gather at all. It is worth being direct about the genuine trade-off this decision represented. This was not a case of switching off a broken, malfunctioning piece of equipment. The low-energy charged particles experiment was, by every available measure, still working exactly as intended right up until the moment it was deliberately powered down, and shutting it off permanently eliminated one of only 2 remaining functioning windows into the physical conditions of interstellar space this specific spacecraft had left. Throughout Voyager 1's journey, this particular instrument had measured the low-energy charged particles, ions, electrons, and cosmic rays, both originating from our own solar system and streaming in from the wider galaxy beyond it, providing critical evidence about the structure of the boundary between our sun's magnetic influence and true interstellar space, including detecting pressure fronts and shifting regions of particle density that no other existing instrument on Voyager 1, Voyager 2, or any other spacecraft currently in operation has the ability to measure directly. NASA's own official announcement of the shutdown acknowledged this loss plainly, noting that the twin Voyagers remain the only spacecraft far enough from Earth to provide this specific kind of information about the true interstellar environment, meaning the scientific window this instrument once provided has now, following its shutdown, simply closed, with no alternative source of comparable data available anywhere else. NASA's own engineering team made this choice anyway, because the alternative, continuing to operate an instrument that had already demonstrated it could contribute to an unexpected dangerous power event, carried a risk to the entire remaining mission that outweighed the genuine scientific value of the specific data that instrument continued to provide. This single incident fits into a considerably larger ongoing effort NASA has been conducting throughout 2025 and 2026, specifically aimed at extending both Voyager spacecraft's operational lives for as long as the underlying physics will realistically allow. Engineers have spent the same period testing an experimental, previously unattempted power redistribution procedure, nicknamed internally the Big Bang, an all-at-once reconfiguration of how electricity flows through each spacecraft's remaining systems, specifically designed to squeeze out additional years of usable power that the raw, unmodified decay curve of the plutonium generators would not otherwise provide. The procedure works by identifying specific components across the spacecraft that could plausibly be run more efficiently, or replaced entirely with lower power alternatives, and switching all of these individual changes over simultaneously, rather than adjusting them one at a time and testing each individual change before moving to the next. Engineers deliberately chose this all-at-once approach specifically because any transition between different power configurations passes through a genuinely unstable intermediate state, and minimizing the total time a spacecraft spends. Passing through that unstable state reduces the overall window during which an automated fault protection response, similar to the one narrowly avoided in February, could potentially be triggered by the reconfiguration process itself. Because any significant change to a spacecraft's power distribution carries genuine risk, exactly the kind of risk the February roll maneuver had just demonstrated, in an unplanned, unexpected way, engineers deliberately chose to test this procedure first. On Voyager 2, which currently carries a slightly larger power margin and sits marginally closer to Earth, making a potential failure marginally less catastrophic to the overall mission. Those tests were conducted in May and June of 2026, and in August of 2026, NASA confirmed the procedure had succeeded, genuinely buying Voyager 2 additional operational time beyond what its unmodified power supply would otherwise have allowed. Engineers have since indicated they intend to attempt the same procedure on Voyager 1, carrying with it a genuine, if uncertain, possibility that the very same low-energy charged particles experiment shut down back in April could eventually be switched back on, should the resulting power savings prove sufficient to safely support it again. Any attempt on Voyager 1 specifically carries an additional layer of caution the Voyager 2 test did not require, given that Voyager 1 had already demonstrated only months earlier a genuine capacity to behave unpredictably during exactly the kind of operational change a major power reconfiguration inherently represents. It is worth pausing to appreciate exactly what this entire sequence of events actually reveals about the genuine, ongoing difficulty of operating a spacecraft this old, this far away, and this fundamentally unlike anything any current engineer originally trained to build or maintain. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, has spoken candidly and repeatedly about the specific nature of this challenge, describing incidents like this one as, in her own words, sort of par for the course at this particular stage of the mission, given that both spacecraft are now operating decades beyond anything their original 1970s mission planners ever anticipated, using onboard computers and control systems that predate the personal computer entirely, and flying through a radiation environment in deep interstellar space that no spacecraft had ever previously experienced, and that no engineer currently working the mission has any direct historical precedent for managing. This is precisely why NASA was not, and arguably could not have been, fully prepared for exactly what happened during that February roll maneuver. A procedure performed safely and predictably for decades suddenly behaved differently, for reasons that likely trace back to the cumulative, compounding effects of nearly 50 years of continuous operation, aging hardware, slowly shifting internal resistances within circuits that have never once been physically inspected or repaired since launch, and a power margin that has grown so thin that even small, previously insignificant variations in performance can suddenly carry genuinely serious consequences. There is no way to test for every possible failure mode in advance on a spacecraft this old and this far away, and no way to send a physical technician to investigate directly when something behaves unexpectedly. Every response has to be calculated, transmitted, and confirmed across a communication delay now approaching a full day in each direction, with genuinely limited room for error given how little operational margin remains. It is worth being honest about exactly how much uncertainty continues to surround this entire situation going forward, since that honesty is exactly what separates a genuine, responsible account of this mission's current status from an artificially reassuring one. The February power drop revealed a genuine, previously unknown vulnerability in a spacecraft engineers already knew was operating on razor-thin margins. And there's no way to guarantee that some other unexpected event, whether during a future calibration maneuver or simply as a consequence of continued gradual aging, will not reveal another such vulnerability in the future. The Big Bang procedure, while successfully validated on Voyager 2, still needs to be attempted on Voyager 1 itself, carrying its own genuine, unavoidable risk, given that any significant reconfiguration of a spacecraft's power systems inherently passes through unstable transitional states that could, in theory, trigger exactly the same kind of automated fault protection response the February incident already came dangerously close to activating. What remains completely certain, regardless of exactly how these specific remaining risks eventually play out, is that Voyager 1 continues to represent one of the most remarkable ongoing achievements in the entire history of human engineering, a machine built using technology from the 1970s, expected at launch to last only a handful of years, still transmitting genuine, scientifically valuable data from beyond the edge of our solar system nearly 5 decades later. The team managing it today did not build it and cannot rely on the original engineers' own direct experience to guide every decision, since so much of what this spacecraft is currently experiencing, this deep into interstellar space, this far past its intended operational lifetime, has simply never happened to any spacecraft before. Every difficult decision, including the permanent shutdown of a functioning 50-year-old instrument in April of 2026, reflects a genuine, considered trade-off, made under real uncertainty by a team working to keep this singular, irreplaceable mission alive for as many additional months or years as the underlying physics will realistically allow. There is also a broader lesson embedded in this specific episode, one that extends well beyond the fate of a single instrument or a single spacecraft. Voyager 1 is currently approaching another entirely separate milestone, expected to cross a distance of 1 full light day from Earth in November of 2026, becoming the first human-made object in history to travel far enough that a signal moving at the maximum possible speed anything in the universe can travel still needs a full 24 hours just to complete the one-way journey home. Every incident, like the one that unfolded in February, every unexpected power fluctuation, every automated safety threshold narrowly avoided, becomes measurably harder to manage as that same communication delay continues to grow. A slow, steady increase in operational difficulty running in parallel with the equally slow, steady decline in the spacecraft's available power. Susie Dodd has described the day-to-day experience of managing this exact combination of constraints in strikingly human terms, comparing a single exchange of commands and responses to sending a message on a Monday morning and simply not hearing anything back until Wednesday. A genuinely strange patience-testing rhythm to operate under, especially when a genuine developing emergency, like the one in February, does not wait politely for that same communication delay to resolve itself. So here is the honest, complete picture of what actually happened, and why NASA genuinely was not fully ready for it. A routine, previously safe calibration maneuver on February 27, 2026, produced an unexpected, potentially dangerous drop in Voyager 1's available power, bringing the spacecraft uncomfortably close to triggering an automated safety response that could have shut down systems unpredictably, with no opportunity for human intervention. In direct response, engineers made the difficult decision to permanently switch off one of the spacecraft's last 2 remaining scientific instruments in April, a genuine sacrifice made specifically to protect the broader mission from a similar and potentially far more serious incident in the future. That same team is now working to test an experimental power-saving procedure on Voyager 1 itself, having already successfully validated it on Voyager 2, carrying with it a real chance that the very instrument sacrificed in April could eventually return to service should the physics and the engineering finally cooperate. Nobody currently managing this mission can promise exactly how the coming months will unfold, and every credible, responsible account of this specific situation has been careful to say so plainly, rather than offering false confidence about a spacecraft that has already demonstrated twice now within the same handful of years its genuine capacity to still surprise the very engineers who know it best. If you want to know whether the Big Bang procedure succeeds on Voyager 1 itself, and whether its silenced instrument ever gets the chance to switch back on, subscribe, and turn on notifications, because this spacecraft's story is still actively being written, one carefully managed risk at a time.